Okay, started recording. Sorry about that. I was running a little bit late today. This is kind of similar to the kind of departure that happened in 133 last semester, where for the whole semester we were, dropping things and measuring masses and stuff, and then all of a sudden it was, waves or gases. This semester it's actually,
Gotta zoom.
similarly in the lab manual they don't give you any explanation for why we're suddenly moving to lasers and stuff. So I wanted to give you the connection based on, and it's a little bit easier to make this semester. Just you have to do a little bit. Why we're suddenly talking about lasers when we've been working with these circuits and electric fields and magnetic fields, and the answer is pretty profound. So I just wanted to, especially because this lab is actually quite easy this week. We're finishing very quickly, so I wanted to talk about some of the theoretical background. So it kind of starts with this thing called the wave equation. You may have seen it in 133 in the wave section, but if not, it's not incredibly illuminating to derive it, but I will give just kind of a little sketch of it. It is apparently in this chapter 15 of the Giancoli book, where you kind of envision things. The way I described it in 133 last year was like, when you're a kid and you take a hose or something connected to, I don't know, a house, and you like whip it, and the wave, rides down to the hose, and you see things, those resonant patterns. The easiest way to derive the equation that describes that is to kind of envision little particles just moving up and down. So they have like at each point in time, they have kind of a harmonic look to them. So one way to do it more succinctly is to divide up the areas so that you're looking at kind of like a string that goes across some region. And you're, so let me just hover over this. I don't think this derivation is the best. It does, it gets there. This is the wave equation. It's the second spatial derivative on the left-hand side of some function. And then we have this 1 over v squared, which we'll describe in a little bit. It turns out to be the speed of the wave, the velocity at which the wave is traveling. And then you have a time derivative. One thing we can notice is we had kind of this time and space derivatives when we were talking about Faraday's law and special relativity, and we'll get to that in just a second. I just wanted to give you a better derivation of the wave equation. This is from that Taylor book that we used last week. Very similar to the book. I just think this geometric way to do things is a little bit better. But again, this is this isn't part of the class, so I just didn't want to spend a ton of time on deriving that. But just to give you an idea of where it comes from. What I did want to show you was, let's see here, how this wave equation relates at all to what I was talking about, over the last couple labs and how it relates to today. So what I'm going to do is start off with Maxwell equations. These are a special version of Maxwell equations that they exist in vacuum. So for instance, if I were to Google Maxwell equations, it would probably have a charge and a current in place of zeros. So for instance, if you look at the dot product of E or D, I guess, let's see, over here, this row over here is the charge in a given space, and this J over here is the current in a given space. However, I'm just going to look at when there are no charges and there are no currents. So here I have the del operator, which is like with a dot. This gives me the scalar quantity, these two equations, and these two equations are the whole of Maxwell's equations. And I'm going to do kind of play a trick here. I'm going to take one of these equations and manipulate it to see what else I can learn from it. And this happens on the Griffiths E&M book around these pages. So I'm going to start with this this equation for the E. So this is the curl of E is equal to the time derivative. So this is the spatial derivative, this is the time derivative. Remember, this is the Faraday's law that we used in the inductance lab. And I'm going to take another curl of it. So I'm going to take a curl of the left-hand side and a curl of the right-hand side. And then I'm going to use this rule that maybe you remember from calculus or algebra. It's called the back minus cab rule. If you have 3 cross products at one time, you can write it as dot products, specifically this kind of arrangement here. So if I do that with this arrangement, I have del cross E, and then I get this. So this is the back, and this is the cab. However, now I can use another one of the Maxwell equations, notably the first one, which tells me that the dot product is E with the del operator, and the del is just, it's kind of like a, let's see if I have it open here. No, the del operator is just, it's kind of like a space derivative, so d dx, but with all the coordinates. So it would be like, instead of df dx, it would be df dx, comma df dy. So it returns a vector back to you. So now that I know that this is 0, I have this equation. So I have the del cross E is equal to this thing called the Laplacian, which is just like the del, except it's the second derivative. So now I have the second derivative in x, second in y, and second in z. Now, I'm going to pull a similar trick that I did when we were doing that inductance lab on this side of the equation. Remember, in the inductance lab, what I did was I said there's no difference between if I integrate first or I derive first. Here, I'm just going to do the same thing with 2 derivatives. I can either take the space derivative first or the time derivative first. So here, I'm going to take this dt outside, and I'm going to bring this curl inside. Now I can use another one of the Maxwell equations, the fourth one, because I know that the cross of B is these 2 constants, which we'll learn about in just a second. Those are the 2 things that we've been using all across this whole semester, and I'm going to explain to you what they are in just a second, because they're not, these kind of coming out of the blue equations or constants in nature. They actually come from something a little bit more fundamental. So now if I plug this thing in, I have that is equal to mu naught epsilon naught time derivative of d. So now what I've done is I've taken a coupled first order differential equation, and what that means, I'm taking one time derivative, or one space derivative, one time derivative, and it has an E and a B. So that's a coupled. First order means there's no squareds, and coupled means it's an equation for E over here and an equation for B over here. But now that I've made all these substitutions, it's just an equation for E. It's a second order uncoupled differential equation. Now, if I compare this to what the wave equation looks like, so I did it for E in this case, but you can do the exact same steps for B. So if I compare this to the wave equation, which read right, oh, I lost it. Here's another derivation of the wave equation that I particularly like. This is a textbook that I used a lot in college. Let's see here. There's kind of a hint at where we're going. E in the B fields. I think this derivation is quite nice. Let me zoom in out on it for you. But yes, so if we compare this equation down here to what we have in the preview document, all we need to do is change this single derivative. So that's a derivative with x. That's only one coordinate. If we do it with all 3 of the coordinates, it's just this thing up here, the Laplacian. So it's x, y, and z. So now I have a 3D wave equation where I'm making the identification that this epsilon naught and mu naught is equal to 1 over v squared based on that equation over there. Now, what happens if I evaluate this stuff? So what if I go over to Wikipedia and I say, oh, okay, I know the value of mu naught and I know the value of epsilon naught. And what happens if I plug those into a calculator? So I'm going to head over to this application called Mathematica. I'm going to enter those two values, and I'm going to see what happens when I calculate that thing. That is exactly the speed of light. So that's where these two constants come from. They're not kind of derived out of nowhere. They're derived based on the fact that Maxwell's equations describe how light propagates. So when we're shining lasers in this lab, light is electromagnetic waves. So those, all these fields and stuff that we've been talking about all semester are waves, and waves that travel exactly at the speed of light. So there is no a radio wave, like any electromagnetic wave travels exactly at the speed of light. So that's just a really cool way that you can view what we've been doing as quite relevant for what we're doing. And in particular, what we're going to be doing in lab is from this area of what's called optics or geometric optics. Here's that same textbook over here again, which gives, the Giancoli book also covers it, but this textbook gives a really nice derivation based on something called optical path length. So it's like N, the refractive index of the material, is kind of how easy it is for something to move through. So for instance, if you shine light on something with a non-vacuum, if you shine light on water or jelly or something, it doesn't travel as quickly as it would through the air or vacuum. So this optical path length is kind of like how hard it is for something to move through something. And I just really like the way they derive these two equations, the law of reflection that we'll use, which they derive right here. Their notation is a bit hard to understand. POQ, that's just a distance. So it's point P, point O, and point Q. And Snell's law they do in a very similar way over here. However, what I thought was really cool was, this is another instance of you guys doing things that's quite difficult. This was my homework from, let's see, a week ago. And I was asked to prove the incident angle is equal to the reflected angle, not based on geometric optics or anything like that, but purely based on electromagnetic waves. So, this was the thing that we were seeing in class. An electromagnetic wave with this kind of polarization comes in, it's reflected, and some is transmitted. And so we were asked to prove Snell's law and the law of refractance, that the angles that it comes in and goes out at is the same. So I just wanted to connect these electromagnetic and electric and magnetic fields that we've been working with all lab to these lasers and the optics that we're going to be working with today. So that is all. Now I'll kind of switch over to, let me just pause on this again, because I think it's a really nice derivation. And they also have some of the kind of focal length, real virtual image type stuff that we do later in lab. Let me make it a little bigger so you can use this as a reference later. And then I'll get to my tips and tricks on the board. This is in particular one of the ones in the lab manual called the thin lens equation. This book was very helpful in college. I don't think we used this one. Yeah. Okay, so I'll stop recording now and get on to the kind of tips and tricks section. And then, oh, okay, we have a chat. Did everyone else mute themselves? That's it. Okay, yeah, sorry about that. Yes, sometimes it's hard for me to, because I mute myself so that I don't hear the reverb. So yeah, sorry about that. I don't know, there should be a way that I can mute people, but I haven't figured it out yet. So let me stop sharing and stop recording, and I'll post this along with the custom discussion question